So we've seen so far how individual pulses can reflect when they hit some sort of fixed end. We've also seen what happens when multiple wave pulses interfere and interact with one another. But what happens when we combine these two concepts? And then we start to get full wave interference patterns. But if we want to see this happen, we have to send multiple pulses of our wave down towards a fixed end. So we're going to imagine that we have a string, and we're going to send multiple pulses of this string towards a fixed end. So these horizontal lines that I've got set up for you kind of represent the rest axis of that string, meaning that if we weren't providing any wave energy to it, it would just have that rest axis and be straight along that line. But in this case, we're going to create some pulses. So I'm going to imagine that I am creating a very pulsy looking wave and sending all of those pulses down towards the fixed end. Eventually, though, I'm going to draw them in my next stage when they finally reached the other end. So they are going to continue all the way down to the end. Now, eventually, though, those first pulses will reach the end and they'll reflect. And we've talked about how they will reflect and form a trough. So suddenly, there will be pulses that start to come back the other way. So this blue one I'm drawing is representing the reflected pulse coming back. And it would just continue coming back the other way. And we should also just label this red one as well, the idea that it's going towards the right. All of those pulses are going towards the right, and the blue ones are working their way back towards the left. But look at what's happening here. Already, we're seeing lots of situations, just in the pulses that have now interfered with the reflected pulses, each one that's interfering is creating destructive interference. And so if that pattern continues, all of the positive amplitudes from the original one get canceled out by negative amplitudes from the reflected one, and vice versa. So if we draw what the result of this would be, well, first we can redraw the original wave. So a nice red wave. And then the reflected blue wave coming all the way back. And it is obviously just going to alternate. So what is that telling us? Well, at each of these spots, directly in between, at these specific locations, these are all node points. And so when all of these pulses are perfectly lined up, where every crest from the original pulse lines up with the trough of the reflected pulse and vice versa, we get destructive interference not just from those particular pulses, but we get destructive interference through the entire thing. So this is an example of a destructive interference pattern, and that's why we're seeing these nodes being set up. So when the incoming wave pulses and the reflected wave pulses all line up in this particular pattern, it'll produce destructive interference. But what we have to remember is that both of these pulses, or both of these waves, are continuing to move in opposite directions. They're not frozen in that position. That's just what they would be doing for one split second. So we have to imagine that the blue one would continue past this point toward the left, and the red ones would continue back towards the right as well. So even though right now, for one split second, they have destructive interference, if we wait just a little bit longer, we'll get a slightly different pattern. So if we now draw it once again, what would happen if I waited a little bit longer? So obviously, originally, when the first few pulses meet the end, they're going to reflect back. But if I wait a little bit longer, eventually, there'll be a split second in time where the troughs and crests will actually perfectly line up with one another. So that every time one is going through a crest, the other is also going through a crest. And when the other goes through a trough, the other follows. So this would be alternating with the situation just above it. So at certain split seconds in time, we would see destructive interference. But now, in this case, all of the waveforms are in phase with one another. They are all overlapping and producing constructive interference. And what we actually get is not one flat, totally straight line. We get a bunch of supercrests. Or you could also think of them as super troughs in the alternate. So in reality, what I'm going to draw in green now is what the overall wave would look like. Because remember, when all those wave pulses overlap, it would produce supercrests and super troughs. So when these overlap, the actual wave that you observe would not look like the red or the blue. It would look like this green one. It would be a great big supercrest and then go way down into a super trough, and then way back up into a supercrest and way back down, and so on. So that green one now is the actual what we call standing wave. And it will appear to stand there because even though the original pulses were in some cases moving to the left and others moving to the right, this wave, as soon as it is set up, it's not going to appear to be moving left or right. It's just going to appear to be alternating between this constructive interference pattern, the bottom pattern, and the destructive interference pattern. And remember, in the destructive interference pattern, we identified a bunch of nodes. But at the split second when all of those nodes are set up, we would actually just see a perfectly flat line along its rest axis. And so standing waves are actually an alternating pattern of total destructive interference and then a split second later, total constructive interference. And what we see is an alternating pattern between a perfectly flat line and these huge supercrests and super troughs. Back and forth, but no actual left or right motion is observed when this pattern is set up. We also have a special name for another point in the constructive interference situation. We say that these points right at the very top and the very bottom are examples of the exact opposite of a node. Instead of being points that are right along the rest axis, they're the farthest possible distance from the rest axis. So we actually call these points antinodes, literally meaning the opposite of a node. So these highest and lowest points are all examples of antinodes. So if we want to find some way to draw out what a standing wave pattern would look like, we know that really it's going to be alternating between a pattern of all nodes and a pattern of all antinodes. In other words, a pattern that has just a flat line and a pattern that has these great big supercrests and super troughs. But if we just draw a wave and represent it as a perfectly straight line, that's not giving us much understanding about the wave at all. So instead of that, what we tend to do if we want to represent what the standing wave looks like is we draw what its antinodes look like. We draw the more constructive interference situation. Because remember, it will just be constantly alternating between the two. And we'll see this visually in class as well, and you'll be able to observe it with some actual moving waves, and that will make it a little bit easier. But for now, as I said, we're going to try and draw these standing waves by drawing what their antinodes look like. And that'll actually be a little bit different depending on if we're drawing it within a fixed end situation or a free end situation. So when I say a fixed end, I'm going to draw the original rest axis that my wave is going to go around, and then I'm going to draw something to stop it at the end. That's my fixed end. With a free end, I'm going to just draw the rest axis, but I'm not going to draw anything at one end to stop it. So that would be like if I took a rope and waved it up and down, but it wasn't attached to anything at the other end. It could freely move at the other end. If I look at just the fixed end situation, we draw the standing wave just as antinodes. Something like that. And so in this case, we can also talk about the fact that it would alternate a little bit. So if we wait a split second after we see this pattern set up, the line would go completely flat. But then a split second later, we would actually see the exact opposite pattern. All of those antinodes would flip their positions. So they would be set up at opposite places. But now, when we see that full wave pattern, we can use that to identify how many wavelengths we're dealing with. So in reality, if we see, for example, 4 antinodes, like we do here, so if I just count the antinodes along the top, we see 1, 2, 3, and 4, or in other words, sort of 4 crests along the top as we see this alternating pattern. What that's telling us is that we actually have 2 full wavelengths. And so if I sort of cut off the wave and just track its motion, I see that I go through 1 full wave cycle to get to here, and then 1 more wave cycle to get to the very end. So I go through 2 full wave cycles, so this entire distance is 2 lambdas, 2 full wave cycles. That's a little bit different if I'd drawn a similar situation, but with a fixed, or with a free end, excuse me. So with a free end, there's nothing to pull the rope back down. If I'm just imagining waving a rope up and down, if there's nothing that it's attached to at the far end, there's nothing to pull it back down to force it to be a node at the end. And so instead of actually ending on a node, it will end on an antinode. And the alternating pattern, which I'll draw in blue, would do the same thing. It would end on the opposite kind of antinode. And so in that case, what I'm seeing in this particular example is even though I'm actually seeing 1, 2, 3 different antinodes, I still need to look closer to identify how many full wavelengths I have. So in this case, it's actually a little bit weird. If I look at my starting point in the wavelength and see that I go through 1 full wavelength by the time I get to here, and I'll just track that to make sure that's 1 full wavelength, yep, all the way through that cycle. Then I go 1 extra piece of the cycle, and that's actually not even a half of a wave cycle, that's a quarter. So sometimes when we're just dealing with a standing wave pattern set up in a free end situation, we might not complete 1 full wave cycle or even 1 half wave cycle. We might end on a quarter of a wave cycle. So this would actually be 1 1/4 of a lambda. That's 1 1/4 wavelengths is what we're seeing. So again, we draw out standing wave patterns. We see how many different antinodes we observe, and we can try and use that then to figure out how many full wavelengths have been set up, and try and use that with some of our other things related to waves to try and understand the motion more generally. That final example that deals with Patty the rodeo clown, we're going to deal with in class. It's a little bit tricky to set up on your own, so don't worry about it so much now, and we'll deal with it in more detail a little later on.